Bismillah ar-Rahman ar-Rahim. We have a special value trilogarithm identity. The arguments of the trilogarithms on the left-hand side are 1/3, -1/3, 3/4, and -1/2. The left-hand side can be expressed in terms of the natural logarithm of 2, the natural logarithm of 3, pi, and zeta of 3. To prove this, we make use of these trilogarithm identities. The second one has been previously studied on this channel. Here, I provide proofs for the first and third identities. The first identity involves the trilogarithm of z and the trilogarithm of 1 over z. We start the proof by making use of the dilogarithm. The dilogarithm of z is the integral u from 0 to z of minus ln1 minus u over u. The trilogarithm is the integral u from 0 to z, the dilogarithm of u over u. The dilogarithm of -1 over y is this integral with z replaced by -1 over y. Differentiate with respect to y, we have this minus sign. The derivative of the upper limit of integration is 1 over y squared. Then we replace each appearance of u in the integrand by the upper limit of integration -1 over y. Simplifying, we get 1 over y, the natural logarithm of 1 plus 1 over y. This is ln1 plus y over y, which is ln1 plus y minus ln y. We have this side and that side. Integrate from 1 to x. From here, we get the dilogarithm of -1 over x minus the dilogarithm of -1 over 1. This is the dilogarithm of -1, which is minus pi squared over 12. The integral of this part is -1/2 ln y all squared. When we use the limits of integration, we get -1/2 ln x squared. To integrate this part, let's use the substitution z equal to -y. We get the integral z from -1 to -x ln 1 minus z over z. This is the integral from -1 to 0 plus the integral from 0 to -x. Making use of the integral representation of the dilogarithm, this integral here is minus the dilogarithm of -x. This one is equal to minus integral from 0 to -1 ln 1 minus z over z dz. This is the dilogarithm of -1. After integration, we get this relation here. The dilogarithm of -x plus the dilogarithm of -1 over x is -1/2 ln x squared minus pi squared over 6. Write this identity using u, divide both sides by u, then integrate from x to 1. The integral u from x to 1, the dilogarithm of -u over u, is processed by doing the change of variables v equal to -u. This is the integral v from -x to -1, the dilogarithm of v divided by v. Swap the limits of integration and multiply by -1. The integral from -1 to -x is the integral from -1 to 0 plus the integral from 0 to -x. The trilogarithm of x is the integral from 0 to x, the dilogarithm of u over u. Thus, this is minus the trilogarithm of -x. This term here is the integral v from 0 to -1, the dilogarithm of v divided by v, and this is the trilogarithm of -1. When we integrate this part, we do the substitution t equal to -1 over u. We get an integral like this one, but there is a minus sign, and -x is replaced by -1 over x. So we get this result here multiplied by -1. This -x is replaced by the reciprocal of x multiplied by -1. The antiderivative of this part is -1/6 ln u cubed. When we use the limits of integration, we get 1/6 ln x cubed. Finally, the integral of this part, u from x to 1, is pi squared over 6 ln x. The sum of these two sides is equal to the sum of these two terms. If we replace x by -x, we get this identity here, which is the first identity we need to evaluate this left-hand side. Now to the proof of the third identity. Differentiate the trilogarithm of -x over 1 minus x. The derivative is -1 over 1 minus x squared. We replace the dummy variable of integration by the upper limit. So we get the dilogarithm of -x over 1 minus x. 1 over u becomes -1 minus x over x. Simplifying, we get the dilogarithm of -x over 1 minus x divided by x times 1 minus x. This is equal to 1 over x plus 1 over 1 minus x. We make use of this identity for the dilogarithm. This allows us to express this dilogarithm in terms of the dilogarithm of x. This is what we get. Now we take the derivative of the trilogarithm of 1 minus x. The derivative of 1 minus x is -1. We also get the integrand with u replaced by 1 minus x. We have this identity for the dilogarithm, which allows us to express the dilogarithm of 1 minus x in terms of the dilogarithm of x. We get this result here. Now we add these two lines. On the left-hand side, we have the first derivative of the sum of these two trilogarithms. On the right-hand side, we have the dilogarithm and logarithm functions. Replace x by u. Integrate from 0 to x. The integral of this side gives the trilogarithm of -x over 1 minus x minus the trilogarithm of 0, which is 0, plus the trilogarithm of 1 minus x minus the trilogarithm of 1, which is zeta of 3. Recall the series representation of the trilogarithm when the magnitude of z is less than or equal to 1, summation k from 1 to infinity, z to the k over k cubed. The trilogarithm of 0 is 0, and the trilogarithm of 1 is zeta of 3. When we integrate this side, the integral of this part from 0 to x is minus the trilogarithm of x. Integral from 0 to x minus pi squared over 6, 1 over 1 minus u du. This is pi squared over 6 ln 1 minus u. When we use the limits of integration, we get pi squared over 6 ln 1 minus x. The antiderivative of minus 1 half ln 1 minus u squared over 1 minus u is 1 over 6 ln 1 minus u all cubed. The last two terms to handle are this one and that one. Together, they have this antiderivative, giving us this term here. Note that the limit of this term as x tends to 0 from above is equal to 0. This can be checked using L'Hopital's rule. Now we have established this trilogarithm identity. Here are the three identities. Recall that in the special value identity of interest, the arguments of the trilogarithm are 1/3, minus 1/3, 3/4, and minus 1/2. If we use the second identity and we want this argument to be 1/3, then z is equal to 1/2. If z is equal to 1/2, the left-hand side here becomes the difference between the trilogarithm of 1/3 and the trilogarithm of minus 1/3. On the right-hand side, we get the trilogarithm of 1/2, the trilogarithm of 2/3, and the trilogarithm of 3/4. The first identity with z equal to minus 3 allows us to express the trilogarithm of minus 3 in terms of the trilogarithm of minus 1 over 3. Let's make use of the second identity again. Rather than using z equal to 1/2, we use z equal to 2. In this case, this argument becomes minus 1 over 3, and this one becomes 1 over 3. On the right-hand side, we get the trilogarithm of minus 1, the trilogarithm of 1/3, and the trilogarithm of minus 3. We can use this relation here to replace this term by those constants and the trilogarithm of minus 1/3. This is what we get. Moving the trilogarithms to the left-hand side, we get that 3 over 2, the trilogarithm of minus 1 over 3, minus 3, the trilogarithm of 1/3, is equal to this bunch of constants. Multiplying both sides by 2 over 3, we get this statement here, denoted by B. Statement A is the result that we get from the second identity with z equal to 1/2. The last thing to do is to use this third identity with z equal to 1/3. We get statement C, which involves the trilogarithms of 1/3, minus 1/2, and 2/3. The target involves, if we look at our current results, they have the trilogarithm of 1/2, they have the trilogarithm of 2/3. If we look carefully here, it seems that we can use A and C to eliminate the trilogarithm of 2/3. So this can go away using A and C. However, we still have to obtain this value here. The trilogarithm of 1/2 is equal to the integral t from 0 to 1/2, the dilogarithm of t divided by t. Let's do integration by parts. If we use the upper limit of integration 1/2, we get the dilogarithm of 1/2 times the natural logarithm of 1/2. We need to take the limit of this quantity as t approaches 0 from above. This limit can be evaluated using several applications of L'Hopital's rule. The good news is that it is equal to 0. We also have minus the integral t from 0 to 1/2 ln t times the derivative of the dilogarithm with respect to t. The derivative is 1 times minus ln 1 minus t divided by t. The trilogarithm of 1/2 is this part plus the integral t from 0 to 1/2 ln t ln 1 minus t divided by t. What is the value of this integral here? This integral requires that we evaluate integral x from 0 to 1, the natural logarithm of 1 plus x all squared divided by x. To obtain this one, we start by this widely used result. If a is a real number greater than minus 1, b is a strictly positive real number, the integral x from 0 to 1, x to the a ln x to the b is minus 1 to the b gamma of b plus 1 divided by a plus 1 raised to the power b plus 1. This is the special case when b is equal to 1. Minus 1 to the 1 is minus 1. Gamma of 2 is 1. Downstairs we have 1 plus a squared. If b is equal to 2, minus 1 to the 2 is 1. Gamma of 3 is 2. Downstairs we get the cube of 1 plus a. What is the integral from 0 to 1 of ln 1 minus x squared over x? Change x to 1 minus x. We get the integral x from 0 to 1 ln x squared over 1 minus x. X is between 0 and 1. We can write 1 over 1 minus x as summation j from 0 to infinity x to the power j. We can then do integration term by term. According to this result here, the integral is equal to 2 divided by j plus 1 to the power 3. This sum is equal to double zeta of 3. What about the integral from 0 to 1 ln x squared over 1 minus x squared? We can use this result here, x replaced by x squared. So our integral will have 2j rather than j. The result is summation j from 0 to infinity, 2 divided by the cube of 2j plus 1. This is the sum of the reciprocals of the cubes of the odd positive integers. Sum is equal to zeta of 3, but we need to subtract the terms involving the even integers. We can take 1 over 2 cubed as a common factor from this bracket. What remains is zeta of 3 itself. Summation is 1 minus 1/8 of zeta of 3. If we account for this 2, this integral here is equal to 7 over 4 zeta of 3. The integral x from 0 to 1 ln 1 minus x over 1 plus x all squared divided by x. Do the change of variables, y equal to 1 minus x over 1 plus x, which implies that x is 1 minus y over 1 plus y, and dx is dy times minus 2 over the square of 1 plus y. When x is equal to 0, y is equal to 1. When x is equal to 1, y is equal to 0. We can use this minus sign here to get our integral from 0 to 1. Note that without the minus sign, dx over x is 2 dy divided by 1 plus y, 1 minus y, which is 1 minus y squared. We get this integral here, which is 7 over 4 zeta of 3. We need to multiply by 2. The final result is 7 over 2 times zeta of 3. The integral x from 0 to 1 ln 1 minus x squared all squared over x can be obtained using the substitution y equal to x squared. We get 1/2 this integral here, so the result is zeta of 3. Finally, we have reached the integral that is needed in evaluating this integral of interest. To get this integral, we write down the natural logarithm of 1 plus x all squared in the following fanciful way. 1/2 the square of ln 1 minus x minus ln 1 plus x plus 1/2 the square of ln 1 minus x plus ln 1 plus x. These two guys together give us ln 1 minus x squared plus ln 1 plus x squared. Since we are interested in this term alone, we subtract the square of the natural logarithm of 1 minus x. So our integral x from 0 to 1 ln 1 plus x all squared divided by x is equal to 1/2 the integral involving the square of ln 1 minus x over 1 plus x. This term is 7 over 4 times zeta of 3 plus 1/2 the integral involving ln 1 minus x squared all squared. The integral is zeta of 3, so we get zeta of 3 divided by 2. Finally, we have the integral involving the square of ln 1 minus x, and this is 2 zeta of 3. Combining our results, this integral is 1/4 zeta of 3. But our interest is not this integral, but that one here, the integral t from 0 to 1/2 ln t ln 1 minus t over t. To get our desired integral, we simultaneously process these 4 integrals. All of them have a domain of integration from 0 to 1/2. The integral of interest is omega 2. The idea here is that we will construct 4 equations in 4 unknowns. Let's start with the sum of omega 1 and omega 3. In omega 1, change x to 1 minus x. In this case, the integrand becomes the square of ln x over 1 minus x, and our integral now is from 1/2 to 1. Doing this change, the integrand is exactly like what we see in omega 3. We can now combine the 2 integrals as one integral from 0 to 1. 1 over 1 minus x can be written as this summation here. If we integrate term by term, we get 2 divided by j plus 1 cubed. This sum is equal to double zeta of 3. In the second step, we take omega 2 and omega 4. Omega 2 is taken as is. In omega 4, we replace x by 1 minus x. The integrand becomes ln x ln 1 minus x over x, like what we see in omega 2, but the integral becomes from 1/2 to 1. The 2 integrals can be combined as one integral from 0 to 1. We expand ln 1 minus x over x. Ln 1 minus x is minus summation j from 1 to infinity x to the j divided by j. Because we have this x in the denominator, ln 1 minus x over x is minus summation j from 1 to infinity x to the j minus 1 divided by j. Integrating term by term, we get minus 1 over j squared. So this summation with the minus sign is zeta of 3. Omega 2 minus omega 1 is the integral x from 0 to 1/2. As a common factor, we have ln 1 minus x over x. Then we have ln x from here, and an extra ln 1 minus x from there. Omega 2 minus omega 1 has this logarithm of x over 1 minus x. Do the change of variables, u equal to x over 1 minus x. When x is 0, u is equal to 0. When x is 1/2, u is equal to 1/2 over 1/2. That's 1. ln x over 1 minus x is ln u. X is u over 1 plus u. So 1 minus x is 1 over 1 plus u, which can be written as minus the natural logarithm of 1 plus u. Dx is du over 1 plus u squared. Simplifying, we get 1 over u times 1 plus u. Together with this minus sign, this is equal to 1 over 1 plus u minus 1 over u. We have two integrals. For this second integral, do the expansion of ln 1 plus u over u. Ln 1 plus u is summation j from 1 to infinity minus 1 to the j, u to the j divided by j. If we divide by u, we have here u to the j minus 1. When we integrate, we get summation j from 1 to infinity minus 1 to the j minus 1 over j times 1 over j squared. This summation is equal to zeta of 3. We need to subtract double the sum involving the even positive integers, which is 1/8 of zeta of 3. Thus, we get 3/4 of zeta of 3. For this integral, we do integration by parts. When we use the upper and lower limits of integration, we get zeros. Then we have minus 1/2 integral from 0 to 1, ln 1 plus u all squared divided by u du. This is the integral we have spent some time on. It's equal to zeta of 3 divided by 4. So here we have minus zeta of 3 divided by 8. Omega 2 minus omega 1 is 5 over 8 zeta of 3. Our fourth equation involving the omegas is omega 1 minus 2 omega 4. This is omega 1. If omega 4 is multiplied by minus 2, it can be written as integral from 0 to 1/2 ln x d the square of ln 1 minus x. Using the limits of integration, we get ln 1/2 cubed minus integral x from 0 to 1/2 ln 1 minus x squared over x. But this integral is exactly equal to omega of 1. Our result is minus the cube of the natural logarithm of 2. Let's summarize our results. To get our special value trilogarithm identity, we found that we need to obtain the trilogarithm of 1/2. The trilogarithm of 1/2 requires that we evaluate this integral here, which is omega 2. Rather than attacking the integral directly, we handled 4 integrals at the same time. We obtained 4 linear equations in 4 unknowns. If we take this result minus that one, omega 2 is cancelled, and we get omega 1 plus omega 4 is equal to 3/8 of zeta of 3. Omega 1 plus omega 4 minus omega 1 minus 2 omega 4. This is 3 times omega of 4 equal to 3 zeta 3 over 8 minus this result here. Divide both sides by 3. Now we know what omega 4 is. We know the sum of omega 1 and omega 4. So omega 1 is obtained. Omega 2 is omega 1 plus 5/8 of zeta of 3. Lastly, omega 3 is 2 zeta of 3 minus omega 1. These are the 4 integrals, and this is the one that we need. Now we have the value for the trilogarithm of 1/2. Recall that we started with 3 functional identities for the trilogarithm. We used them to obtain these 3 statements A, B, and C. Our target expression does not involve the trilogarithm of 2/3. It is here multiplied by 2. It is there multiplied by minus 1. What we do is we multiply A by minus 1/2, multiply C by minus 1, and add. When we do this, this term becomes minus the trilogarithm of 2/3, and this one becomes the trilogarithm of 2/3. When we add, these go away. We know what is the trilogarithm of 1/2. The last step to obtain our identity is to add minus b to this mix. After simplifying and using the value of the trilogarithm of 1/2, we get our desired result. This linear combination of trilogarithms in terms of ln2, ln3, pi, and zeta of 3.